Okay, so continuing on with our lecture, we're going to look next at thermochemical equations. So thermochemical equations relate the energy of a reaction. So let me just get this set up really quickly. Okay, so thermochemical equations relate the energy of a reaction to the quantities of reactants and products involved in that reaction. So the equation must be balanced, but you can use fractional coefficients for thermochemical equations. The quantities present are presumed to be in moles, not in molecules. So for example, if you see an enthalpy, it has the units of kilojoules per mole. Now, the key thing to keep in mind, kilojoules per mole of what? And that's really important to think about. So the delta H provided for a particular reaction is given for that exact stoichiometry and those exact reaction coefficients along with the exact physical states shown in the chemical equation. So this enthalpy is specific to the exact number of each molecule that reacts, the exact number, the exact coefficients for each of our chemical species, and the exact physical states for each chemical species. Okay? Now, one thing that is really important to keep in mind is that we can write this reaction enthalpy in terms of each of our reactants. The way that we do that is we take the reaction enthalpy and we divide it by our reaction coefficient. So for example, this reaction generates 241.8 kilojoules per mole of water, 241.8 kilojoules per 1 mole of hydrogen. Now, if we look at the coefficient in front of oxygen, it has a coefficient of 1/2. So if we want to calculate the enthalpy per every 1 mole of oxygen consumed, we divide our enthalpy by the coefficient of 1/2, and that gives us 483 kilojoules per mole of oxygen. So the key thing I want you to keep in mind is that the delta H in terms of kilojoules per mole can be different for different reactants in your chemical equation. Because the coefficients are inherently going to be different in many chemical reactions. Okay, so this is how you write reaction enthalpy in terms of each of your indicated reactants. Let's look at another example, and let's try to write the enthalpy of reaction in terms of each reactant and product. So for example, if our general enthalpy is 815.5 kilojoules, then the delta H reaction, let's write in terms of aluminum first. We have 815.5 kilojoules over 2 moles of aluminum, and that gives us an enthalpy of reaction associated with aluminum in this chemical reaction. So that gives us 815.5 over 2, which in turn gives us an enthalpy of 407.8 kilojoules per mole of aluminum. We can repeat this process for iron oxide. So we have 815.5 kilojoules. One moment. So the enthalpy of reaction for aluminum, as we discussed, was 815.5 kilojoules over 2 moles of aluminum. We punched that into our calculator, and that gave us an enthalpy of 407.8 kilojoules per mole of aluminum. Okay, the enthalpy of reaction with respect to iron oxide, we have 815.5 kilojoules. We divide by 1 mole of iron oxide, and that gives us 815.5 kilojoules per every 1 mole of iron oxide. We can look at the same process for iron. The enthalpy of reaction would be 815.5 kilojoules over 2 moles of iron, which gives us 407.8 kilojoules per mole of iron. And finally, the enthalpy of reaction with respect to aluminum oxide would be 815.5 kilojoules per 1 mole of aluminum oxide. So by looking at our overall reaction enthalpy and our reaction coefficients, we can write out the enthalpy of reaction in terms of each of our reactants consumed and products generated from a chemical reaction. Does this make sense to everyone so far? And again, the key driving factor behind this is that different reactants are consumed in different stoichiometric amounts as the chemical equation proceeds. Any questions? So to test our understanding, let's look at the following reaction and let's write the enthalpy of reaction in terms of each reactant and product. So let's spend about 4 minutes on this example. I'd like you to write the enthalpy of reaction in terms of each reactant and product. And we'll discuss this example momentarily. We'll spend about 4 minutes on this example. Don't be shy to write any questions that you have in the chat or to provide your proposed solution to this problem in the chat. And if you have any questions, don't be shy to unmute and ask them verbally or to share your questions in the chat. And the responses I'm seeing in the chat look good so far. And we'll discuss this example in about another 2 to 3 minutes. Give me 1 second just to reset OneNote as I'm noticing a small amount of delay. Allow me 1 second just to reset OneNote. Just to prevent delay when we go over the solution. So let's continue working on this example and then we'll discuss in about another 2 to 3 minutes. Don't be shy to message me with your proposed enthalpies of reaction for each of the reactants and products in this chemical equation. And we'll discuss this example in about another minute to a minute and a half. Okay, so let's look at this example. So the enthalpy with respect to C2H4 would be negative 2,486 kilojoules for every 1 mole of C2H4. Okay. The enthalpy of reaction with respect to fluorine is 2,486 kilojoules for every 6 moles of fluorine. And that in turn gives us negative 414.3 kilojoules per mole of fluorine reacted. Our enthalpy in terms of CF4 would be 2,486 kilojoules for every 2 moles of CF4. And that gives us negative 1,243 kilojoules per mole of CF4. Finally, the enthalpy with respect to hydrofluoric acid generated is 2,486 kilojoules for every 4 moles of hydrofluoric acid produced. And that in turn gives us 621.5 kilojoules per mole of hydrofluoric acid generated. Is everyone comfortable with these calculations? Any questions on these calculations so far? So let's continue on now and let's apply this idea and let's start to look at what happens when you begin to modify your chemical equation. So suppose, for example, that if you multiply your reaction coefficients by a whole number, the reaction enthalpy also gets multiplied by that whole number. So for example, H2O leads to H2 plus 1/2 O2. This has an enthalpy of 241.8 kilojoules per mole. Okay, so if we multiply all of our coefficients by 2, then our enthalpy also gets multiplied by 2. And in turn, our enthalpy doubles if we double our coefficients. Now, the enthalpy of a reaction also really closely depends on the physical states of each reactant and product. So, as you notice, if we compare a reaction involving gaseous water to a reaction involving liquid water, there is a relatively large difference in the enthalpy associated with each reaction. And that difference is the enthalpy associated with a phase change. In this case, this is the enthalpy of vaporization that is the main difference between these two reaction enthalpies. We'll talk more about that later. The key thing I want you to really hone in on is that you need to be meticulous about your physical states in thermochemical reactions because the physical state of each species directly impacts the enthalpy associated with that species. So let's do an example. So if we're given the following reaction, we're asked to write the enthalpy for this new reaction below. So as we can see from this new reaction, all of our coefficients were multiplied by 5. Ergo, our enthalpy will be our original enthalpy times 5. And that in turn gives us our new enthalpy for this reaction, 198.9 times 5. And that in turn gives us 994, rounding, it would 994.5 kilojoules per mole. Oh, well, or just kilojoules in this case, since it's the overall reaction enthalpy and we haven't written it in terms of any of our reactants just yet. Does it make sense how we modify an equation's reaction enthalpy when we modify our coefficients? So
Wait,
let's,
why did you do times 5?
because looking at our coefficients, what have all of our reaction coefficients been multiplied by? What did we multiply all of our reaction coefficients by when we went from this top equation to our bottom equation?
By 5.
Yep, and because we multiplied all of our coefficients by 5, our enthalpy overall for this reaction also gets multiplied by 5.
What happens if the coefficients were all different numbers?
Then it would be an entirely different equation. There would always be a common factor for adjusting your reaction coefficients if you're looking at scaling up or down a reaction to a different number of moles of each of your reactants. If the actual coefficients start to change and become different in the new equation, then we have to calculate the enthalpy using a slightly different method. Does that make sense?
Yeah, thank you.
Perfect, perfect. So let's try to apply what we've seen in this first example. And let's take a look at, we're given the following reaction above, and I'd like you to calculate the enthalpy for this reaction below. So your job is to figure out what did I multiply all of my coefficients by to generate this new chemical equation. And once you have that information, you can calculate the enthalpy of this new reaction. So we'll discuss this example in about 3 minutes, and don't be shy to message me with your proposed responses or any questions that you have. Yep, the response I see in the chat looks reasonable so far. Yep, the responses I'm seeing in the chat look great so far. Spend a few more minutes working on this example. And we'll discuss this example in another minute. Okay, so let's discuss this example. So if we went from a coefficient of 2 to 7, we have multiplied by the number 7 over 2. So if we're calculating our new enthalpy, we take our original equation enthalpy and we multiply it by our common factor, which is 7 over 2. That in turn gives us an enthalpy (1,204 times 7 over 2, which gives us negative 4,214 kilojoules. So this is the new adjusted enthalpy for this modified reaction equation. Does that make sense to everyone so far? Does that make sense to everyone so far?
Yeah.
Okay, perfect. So let's look at another way that we can utilize our chemical equation. And in this case, we're going to be able to relate the moles of a species that reacts to the amount of energy absorbed or released in our chemical reaction. So we're asked to go from the moles of acetylene in this case to the kilojoules of energy. So our conversion factor in this case to go from moles of reactants or products to the amount of energy absorbed or released is our enthalpy of reaction. So if we have 1 mole of acetylene, looking at our chemical equation, we have 2,511 kilojoules released per how many moles of acetylene that react? How many moles of acetylene are reacting in this chemical equation? How many moles of acetylene are reacting in our prototypical chemical equation?
2.
2, exactly right. Okay, so this conversion factor is obtained by looking at your chemical equation, writing the enthalpy over the reaction coefficient for that reactant. Now, if we punch this into our calculator, that in turn gives us negative 1,256 kilojoules total. The moles of acetylene cancels out. Does that make sense to everyone so far? Does everyone see how we can use the enthalpy for a given chemical equation to calculate the energy absorbed and released by the chemical equation, or by the chemical reaction in this case? So in order to test our understanding, as I see everyone seems relatively comfortable with this idea, let's try to showcase another way that we can use this idea of reaction enthalpy. So if 50 kilojoules are released by the chemical reaction, we're asked to figure out what mass of oxygen reacted. So in this case, we're going to go from kilojoules of energy to the moles of oxygen that reacted to the grams of oxygen that reacted. Okay, when we say 50 kilojoules are released, what sign should I put for my heat? What is the sign of my heat value? Is it going to be positive or negative if heat is released? Is it going to be positive or negative if we're releasing energy? Negative, exactly right. So our heat associated with this reaction is negative 50 kilojoules. Okay, in terms of our conversion factor, looking at our equation, again, we have negative 50 kilojoules times negative 2,000. So let's try to think up a conversion factor to go from energy absorbed or released by the reaction to moles of oxygen. And now my question to all of you is, how many moles of oxygen are reacting? And when those moles of oxygen react, how many kilojoules of energy do we absorb or release? So let's fill in the numbers. So looking at our equation, how many moles of oxygen are reacting in this thermochemical equation?
5.
5, exactly right. So we put a 5 up here for our moles of oxygen. Moles of oxygen is on top because we want to convert to moles of oxygen. In terms of energy released by this thermochemical equation, for this exact equation here, where 5 moles of oxygen react, how much energy is released? How much energy is released?
Negative 2,511.
Yep, exactly right. So we plug that in. Okay, kilojoules of energy cancels, and that gives us the moles of oxygen. And just to complete this in a one-line format, we know that we have 32 grams for every 1 mole of oxygen. Remember, when I say the word oxygen, when we're talking about chemical reactions, we're referring to the molecular species. So now our moles of oxygen cancels. We're left with grams of oxygen. And all we have to do is just enter this one line calculation into our calculator. So we have 50 times 5 over 2,511 times 32, which gives us 3.2 grams of oxygen. Note, and this is really important, you cannot have a negative mass. There's no such thing as a negative mass or negative moles. So if for some reason you get a negative number out, you will likely need to go through and revise your calculations. Does that make sense? So always make sure you have like a logical check that you can use to look at your answer and just make sure that it is logically cogent. Does this example make sense to everyone? The only thing that's new is we're beginning to use our chemical equation to convert between the energy absorbed or released by our reaction and the moles of a reactant or product that participates in that reaction. Okay, so let's look at the following. Let's look at the following reaction. I'm just going to zoom out a little bit. And let's look at the following problem. Let's spend about 5 or 6 minutes on this example. So in the first case, we're asked to figure out the kilojoules of heat absorbed when 44 grams of carbon dioxide reacts. And then in the second example, if 100 kilojoules of heat are absorbed, I'd like you to tell me what mass of carbon dioxide reacted. So let's spend about 5 to 6 minutes on this example, and don't be shy to message me with questions or with your proposed responses via the Canvas chat or Zoom chat, or don't be shy to unmute and ask your questions verbally. And we'll discuss this example in about 5 to 6 minutes. And we'll continue working through this example, and really don't hesitate to propose your responses in the chat, and I'd be happy to provide feedback. And one of the responses that I see in the chat looks perfect. It's exactly right. Don't be shy to message me with your responses, and I'd be happy to provide feedback. And we'll discuss this example in about another 4 to 5 minutes. And if you have any questions or want to submit a proposed response, again, don't hesitate to type it in the chat. And in turn, we'll discuss this example in about another 3 to 4 minutes. And the response I see in the chat for part 2 looks perfect. And we'll talk about this example momentarily. And if you have any questions, don't hesitate to ask. And we'll discuss this example in about another 2 minutes. Okay, so let's discuss this example. So we're going to go from the grams of carbon dioxide that reacts to the moles of carbon dioxide to the kilojoules of energy absorbed or released. We know if we have 44 grams of carbon dioxide, we know that in 1 mole of carbon dioxide, we have 44 grams. We also know, looking at our chemical equation, that we have 2,816 kilojoules of energy absorbed per how many moles of carbon dioxide? How many moles of carbon dioxide are reacting in this given thermochemical equation? How many moles of carbon dioxide are reacting in this given thermochemical equation?
6.
6, exactly right. So now we have all the data we need to punch into our calculator. So we have 44 over 44 times 2,816 over 6, which gives us 469.3 kilojoules that we round to 470 kilojoules. It's positive, so we have 470 kilojoules being absorbed as this reaction takes place. Okay, any questions on this first part? Any questions on this first part? If not, we have 100 kilojoules absorbed by the chemical reaction, and we're asked to figure out the mass of carbon dioxide. So we're going to go from 100 kilojoules to the moles of carbon dioxide to the grams of carbon dioxide. Okay, so now that we have 100 kilojoules as our input, absorbed, it's a plus sign. Absorbed and enthalpy or heat is positive. Released, negative. Okay, so we have 100 kilojoules. We know that in 1 mole of carbon dioxide, well, how many moles of carbon dioxide react and how much heat is absorbed? So looking at our earlier ratio, we see we have 6 moles of carbon dioxide that react per every 2,816 kilojoules of heat that are absorbed. We also know that we have 44 grams per mole of carbon dioxide. And that in turn gives us 9.375 grams that we round to 9.4 grams of carbon dioxide. Does this example make sense to everyone? Everyone comfortable with this example so far? Okay, the responses I saw so far in the chat looked perfectly reasonable so far. So let's talk a little bit about calorimetry of chemical reactions, and let's tie together this idea of stoichiometry, calorimetry, and mass to mole conversions. So these are some examples that you may expect to see on an actual exam. These are of reasonable difficulty and they'd be worth somewhere around 10 to 15 points. So meals ready to eat in the military can be heated on a flameless heater. This is driven by a reaction of magnesium and water. So we have the following chemical equation with the following reaction enthalpy. We're asked what quantity of magnesium is needed to supply the heat required to warm 25 milliliters of water from 25 to 85 degrees Celsius. And we can assume the density of the solution is the same as that for water of 25 degrees Celsius. So at 25 degrees Celsius, the density given is 1 gram per mil. Okay, so first and foremost, we need to think a little bit about what we need to do in this problem. So our end goal is to calculate the grams of magnesium. Okay, we're going to get that from the moles of magnesium, and we're going to get the moles of magnesium from the kilojoules associated with our reaction. And in turn, we can figure out the heat associated with our reaction by the heat absorbed by our water. Okay, so we know that Q reaction is equal to negative Q water. Okay, and we know that Q water is -1 times the mass of water times the specific heat of water times T final minus T initial. Do we have each of these pieces of information? Do we have each of these pieces of information? Can we calculate the heat absorbed by our water sample? Yes or no? Just like in classic calorimetry. Yeah, we definitely can. So then our Q reaction is equal to -1 times the mass of water, which is 25 milliliters times 1 gram per mil, times the specific heat of water, which is 4.184. Oops, let me rewrite that. 4.184 joule per gram degrees Celsius times T final, which is 85 degrees Celsius, minus T initial, which is 25. That in turn gives us a heat of reaction of 25 times 1 times 4.184 times 60. That gives us a heat of reaction of negative 6,276 joules. And we know that in 1 kilojoule, we have 10 to the third joule, which gives us negative 6.276 kilojoules. Okay, so this is the heat absorbed by our water, and the negative sign converts it to the heat released by our reaction. Okay, so starting with 6.276 kilojoules, we are now going to try to convert this into the moles of magnesium that reacts. So how many moles of magnesium react and how many kilojoules of energy are produced? So looking at our equation, how many moles of magnesium react? How many moles of magnesium react in our thermochemical equation? How many moles of magnesium react in our thermochemical equation?
1.
1, okay. Continuing on, how many kilojoules of heat are released by this reaction? How many kilojoules of heat are released by this reaction?
Negative 353.
Exactly right. So let's plug that in. So if we punch that into our calculator, we have 6.276 over 353, which gives us 0.01778 moles of magnesium, okay? And then to calculate the grams of magnesium, we take 0.01778 moles of magnesium times 24 grams of magnesium in 1 mole of magnesium, which gives us 0.42. Let me look at my input data. We only have 2 sig figs in our inputs, so 0.43 grams of magnesium. Okay, now one thing that I do want you to keep in mind in this problem is that the magnesium is being converted into magnesium hydroxide. However, it's not soluble and we're not given any information on the specific heat. So we can assume that heat transfer to magnesium is negligible. Yeah, so we don't have to worry about the fact that that mass of magnesium hydroxide is absorbing a little bit of heat. One trick that you can use just to check is just to compare the mass of magnesium to the mass of water. And we have 0.43 grams of magnesium compared to 25 grams of water. So in terms of a percentage, it's going to be less than 5%. Turns about 1.7%. So then the mass of magnesium is negligible in calculating heat absorbed by the mixture. Essentially what this is saying, and what I'm trying to convey to you here, is that the magnesium, when it reacts, makes magnesium hydroxide, and that can absorb heat. However, the specific heat is going to be nowhere close to that of water. And even if all of the magnesium hydroxide happened to dissolve and contributed significantly to the heat absorption process, it would only be a 1.7% difference at most. So then, with that idea in mind, we can assume that the extra mass of our solution from magnesium is going to be negligible. There are cases where the added mass of reagent will not be negligible, such as, for example, when you mix an acid and a base together. We've seen examples of that before. But for these types of problems where you have to do stoichiometry, typically the mass of an added solid or reagent you can neglect in your heat transfer expression. Is everyone comfortable with these examples? As you see, we just combined the calorimetry calculations that we're so familiar with the heat to mole stoichiometry calculations that we just discussed. So this chapter is really quite beautiful in that it links a lot of concepts in chemistry together and really showcases the application. This is something that you may practically do when you're out camping, or if you need to cook something and you don't have a stove, you may say, well, how many little pieces of magnesium do I need to use? How much camping fuel do I need to bring with me? So this is very much practical in nature, in my opinion. So as I saw everyone's quite comfortable with this example, let's now take a look at the following example. This is quite a famous or infamous reaction known as the thermite reaction. So this is used to often melt locks, melt door mechanisms, and it can be used to cut through steel and other metals because it generates a pretty egregious amount of heat. From this, I'd like you to calculate the mass of iron that we generate from this reaction when enough heat is generated to warm 50 grams of water from 298 Kelvin to 463 Kelvin. And just because we're in kelvins, I'm going to show you a little trick. The specific heats in Celsius are the same as the specific heats in Kelvin. So the specific heat of water is 4.184 joule per gram Kelvin. And that's because Celsius and Kelvin both follow the same linear conversion factor. If you want, you can convert to Celsius, but what I'm telling you is you don't have to. Okay, so let's take about 5 to 6 minutes to work on this example. And the key thing is try to identify how can I figure out the heat of my reaction, and then in turn, you can relate the heat of reaction to the quantity of your reactants and products. So we'll discuss this example in about 5 to 6 minutes. And the responses I see in the chat look great so far. And if you have any questions, don't be shy to ask in the chat, and really don't be shy to write your proposed solutions. As a side note, all of these examples that we cover will be integrated in Canvas over the next few days. So that way you have another pool of practice questions for your exam.
Hey, Professor, I was wondering if we were going to know what the lab exam will look like.
Yes, I'm still working on the details and talking with the other section instructors, and I'll try to give you information as soon as I have some updated information for you.
Okay, thank you.
And we'll discuss this example in about another 3 minutes. Don't be shy to write your proposed responses in the chat, and I'd be happy to provide feedback and suggestions moving forward when solving these problems. So looking at the setup proposed in the chat, once you have the moles of iron, you can convert to mass just using the molar mass. I would double check your molar mass, and remember, molar masses are always written with respect to 1 mole of material. Other than that, the setup looks promising so far. And we'll discuss in another 2.5 to 2 minutes. Yep, the setup looks exactly right now in the chat. And we'll discuss this example in another minute to a minute and a half. Okay, so let's discuss this example. So we're going to go from the heat of reaction to the moles of iron. to the grams of iron, and we can get the heat of reaction from the heat associated with our water sample. So as Q reaction is equal to negative Q water, we have -1 times the mass of water times the specific heat of water. I'm going to write it in joule per gram Kelvin, times T final, which is 363 kelvins, minus T initial, which is 298 kelvins. So that gives us a heat of reaction equal to, let's punch this into our calculator. So we have 363 minus 298, 363 minus 298 times 4.184 times 50, which gives us negative 13,598 joules. And we know that in 1 kilojoule, we have 10 to the third joules, which gives us negative 13.598 kilojoules. Okay, so then now that we have the heat of reaction, so negative 13.598 kilojoules, we know, looking at our reaction enthalpy, we have negative 848 kilojoules. And how many moles of iron are reacting in our thermochemical equation to generate that 848 kilojoules of heat? How many moles of iron are reacting? Two. Yep, perfect. Okay, and we know for the molar mass, we have 55.85 grams of iron in 1 mole of iron. So punching this into our calculator, we have 13.598 times 2 over 848 times 55.85. And that in turn gives us 1.8 grams of iron. Does this example make sense to everyone? Any questions on this example? Any questions on this example?
I had a question about the last example.
Sure, sure.
So for the last one, so we did the one that we just did all on one line, but could we have done that for the last one too and still get the same answer?
Yes, yes. Yep.
Okay.
All of these can be done as a one-line conversion. The only reason I split this one up into 2 lines is just to be explicit as to what's going on in each step. But yes, you can write it all from start to finish. And actually, on an exam and organizationally, I personally find the one-line conversions easier to look at, and if I want to go back and check my work, it's easier just to see, oh, okay, I put these 3 things in and all I have to do is just enter it in my calculator rather than carrying it through multiple steps. Mm-hmm.
Okay, thank you.
Yep. Any other questions on this example? These are always good problems because they really showcase the application of multiple different skills. If there aren't any other questions, let's move on now to internal energy and chemical reactions. Okay, so internal energy and chemical reactions. So under constant pressure, that's our stipulation, the enthalpy and internal energy are related to each other by this P delta V term. Okay, so if we're looking at the following reaction, we're asked to figure out the value of delta E if 89.5 grams of ethylene and 125 grams of hydrochloric acid are allowed to react at atmospheric pressure and the volume change is negative 71.5 liters. Okay, there's a lot to take in here, and let's think a little bit about what we have to do. So if I want to calculate internal energy, I need the heat and the work, okay? I can calculate my heat by taking the number of moles times our enthalpy, and I can calculate my work by taking negative P delta V. Now, if you're really clever, you can even avoid having to use these masses. But we're going to showcase the traditional solution first. There's no need to get fancy. Okay, so in terms of what we know, we know that the pressure is 1 atmosphere and our delta V is negative 71.5 liters. Oh, is everyone able to hear me consistently now? Are there any issues with the audio now? Just to check, can I get a response in the chat? Is the audio restored to consistency now? Can everyone hear me okay? Okay, so in terms of what we're trying to do, internal energy is the sum of heat and work. So in terms of calculating heat, we're going to take the number of moles times our enthalpy. For work, we're going to take the pressure times the change in volume. So with this established, we can calculate work since we know the pressure and we know our volume. So now what we're going to do is we're going to focus in on this N term. So N is equal to the moles of reactant that reacts. Now I know this seems like a bit of a redundant statement, but if something doesn't react, it's not going to generate heat. So then N can be thought of as the moles of limiting reactant. Now with this hint in mind, my question to you is, looking at these two masses, do we know at the onset if we have a limiting reactant? Do we know if we have a limiting reactant? So just like any chemical equation problem, any stoichiometry problem, do we need to figure out if we have a limiting reactant? Do we need to figure out if we have a limiting reactant? Yes or no? Yes. So even though it's not explicitly stated, if you're given masses of each reactant, you need to check that there's a limiting reactant and identify it. Otherwise, you can't complete these calculations. So to do that, we're going to take our grams of ethylene, which is C2H4, convert it to the moles of ethylene, and then convert it to the moles of our product. Okay, if we have 89.5 grams of ethylene, in 1 mole of ethylene, we have how many grams? How many grams are present in 1 mole of ethylene? What is the molar mass of ethylene? 28. Yep, exactly right. Okay, and now how many moles of ethyl chloride do we make per mole of ethylene? What is our mole to mole ratio? 1 to 1, perfect. So that in turn gives us, for our expected amount, expected yield of ethyl chloride, we have 89.5 over 28. And that in turn gives us 3.20 moles of ethyl chloride. Okay, let's do the same calculation. Except this time we'll start from the grams of hydrochloric acid and calculate the expected yield of ethyl chloride. So to do that, we're going to take 125 grams of hydrochloric acid. We know that we have 1 mole of hydrochloric acid per 36 grams. And we know, looking at our stoichiometry, again, we have a 1 to 1 stoichiometry of product to reactant. So in this case, the stoichiometry is relatively straightforward. In other problems, the stoichiometry may not be as obvious. So this gives us 6.67 moles of C2H5Cl. Okay, so based on this information, which reactant is limiting? So based on this information, which reactant is limiting? Which reactant produces the least amount of product? Oh, let me try punching this into the calculator one more time. Sometimes my calculator likes to accidentally carry over a digit. Yep, this should be 3.47. Yep. So comparing our moles of product, ethylene is our limiting reactant. So we're just going to put a box around that. So ethylene is limiting. So then, in terms of calculating heat, so the heat of reaction, we're going to take our moles of limiting times our enthalpy. So in this case, we have 3.20 moles of ethylene reacting with our enthalpy. And looking at our enthalpy in this case, as the ethylene reacts, it generates 72.3 kilojoules of energy per every 1 mole of ethylene that reacts. That in turn gives us a heat of reaction, 3.20 times 72.3, of negative 231.36 kilojoules. Okay, now we can calculate the work of our reaction by taking negative P delta V. Our pressure is 1 atmosphere, and we already know that in this equation, our volume change is 71.5 liters. Negative 71.5 liters. So that gives us a pressure volume change in units of liter atmosphere. So we're going to convert this into joules. We have 101 joules per 1 liter atmosphere. And we know in 1 kilojoule, we have 10 to the 3rd joule. That in turn gives us a value of work for this chemical reaction of 71.5 times 101 over 1,000. That gives us 7.22 kilojoules. Okay, now we know that the change in internal energy is equal to Q plus W, heat plus work. So we have negative 231.36 kilojoules plus 7.22 kilojoules. So let's punch that in. That in turn gives us negative 224 kilojoules. So this is the overall change in internal energy for this reaction. So just to summarize, we identified our known information. We knew the pressure, we knew the volume. We wrote out expressions for heat and work, the two pieces of information we need to calculate the change in internal energy. Then we calculated the heat of reaction, and in turn, we calculated the work associated with our reaction. We added our heat and work together to give the change in internal energy. Key thing, be on the lookout for limiting reactants. So, any questions on this example? Any questions on this example? Is everyone comfortable solving these types of problems? Do these types of problems make sense? Yes. You had a question? Yes. Yes. For the multiplication step, yes. Yes, yes, yes. So if there were 2 moles of ethylene in our chemical formula, it would be divided by 2. But since looking at our thermochemical equation, the enthalpy is provided with respect to 1 mole of ethylene, we put a 1 under it. Does that make sense? So again, just like our previous examples, this conversion factor is written based on your reaction stoichiometry and your reaction coefficients. And that's a really important point, actually, that I'm going to make sure that we're comfortable with in the next example. Any other questions before we work on a group problem-solving example? Okay, so if not, let's take a look at the following problem. And I'd like you to calculate the change in internal energy when 104 grams of, in this case, acetylene reacts with 480 grams of oxygen at 1 atmosphere at 20 degrees Celsius. And our volume change is negative 144.2 liters. So let's spend about 6 to 7 minutes on this example, and then we'll come together as a group to discuss. So let's keep working through this example. So to give a sense of what internal energy represents, since I saw that question in the chat, internal energy is a the best way to think of internal energy is that it's a representation of the ability of a substance or the ability of something to perform work or release heat under certain conditions. So essentially it's a representation of the potential of an object to perform work or release heat. Internal energy is different from enthalpy because enthalpy enthalpy is underpinned by the heat at constant pressure rather than constant volume, but also enthalpy has this, I guess you can call it a displacement term, where it's reflecting the fact that to put something into an ambient pressure, into a space under an ambient pressure, you're displacing a certain volume of space. And as a result, it costs energy to just have an object, to quote unquote place an object in that region of space. Does that answer your question on, so enthalpy and internal energy are different. They're based on different conditions and different measured conditions for how you measure the heat of reaction. In terms of calculating the heat of reaction, you use your enthalpy, your chemical equation, and the moles of limiting reactant. So we'll keep working on this example for another 4 to 5 minutes. And don't be shy to submit your proposed responses in the chat. Did that help make a little bit clear the explanations that I provided? Did I answer the questions in the chat sufficiently? Or do you have any follow-up questions that I can address? Essentially, think about enthalpy and internal energy as a measure of the potential of something to do work or release heat. So the change in internal energy, I'm asking for the delta E, which, as we remember from our previous discussions, is heat plus work. So you'll need to calculate the heat of reaction and the work associated with this chemical reaction. The assignment for the limiting reactant that I see in the chat looks perfect. And for the astute observers, you may notice that our moles of gas are decreasing. So inherently, the reaction will contract in volume. But one thing to keep in mind, whatever moles of a reagent that you're using for your limiting reagent, your enthalpy is kilojoules per mole of a reactant or product. So you need to account for the stoichiometric coefficient. Yep, exactly right. Exactly right. The response I see in the chat looks perfect for the heat calculation. Now you have to combine that with the work calculation, and you have your internal energy expression. And we'll discuss this example in about another 2 to 3 minutes. Yep, that's the, wait, where's the, why is the number so small? The enthalpy is already in kilojoules. Yep, the enthalpy is already in kilojoules, so you don't need to divide. Yep, exactly right. Yep, exactly right. Yes, but for work, make sure to convert from liter atmosphere into units of kilojoules. This is why it's always important to write out the units. As we want a little more time, we'll discuss this example in about another 3 to 4 minutes, just to give everyone a chance to work through these problems. As you notice, a one sentence problem requires a lot of unpacking, but we actually, these problems are quite information rich. So we have all the tools we need. We just have to organize everything accordingly and be really careful with our units. But I'm really pleased with the responses I'm seeing in the chat so far. Let's try to get a few proposed responses. Yep, and the response I see in the chat for the work calculation looks good. Let's try to get a few more responses in the chat, and then we'll discuss this problem in full momentarily. And the response I see in the chat for the change in internal energy looks good. For the change in internal energy, remember that when you're calculating heat, the heat is based on the enthalpy and your stoichiometric coefficient for whatever reactant you chose. So remember to account for the stoichiometric coefficients in your enthalpy expression. So let's discuss this example and let's provide some clarification. So first and foremost, for our limiting reactant calculation, we know that if we have 104 grams of acetylene, we know that in 1 mole of acetylene, we have a total of 26 grams, and we know that we make 2 moles of water per every 2 moles of acetylene. Okay, so punching that into our calculator. So we have 104 over 26. That gives us, whoops, one moment. That gives us 4 moles of acetylene. Okay, let's look at oxygen. We have 480 grams of oxygen. We know that in 1 mole of oxygen, we have 32 grams, and we know that we have 2 moles of water per every 5 moles of oxygen. And that in turn gives us 6 moles. Oh, sorry, this should be moles of water. 6 moles of water expected. So which reactant is limiting? Which reactant generates the least amount of product? Which reactant is limiting? Which reactant is limiting? Acetylene, exactly right. So acetylene is limiting, and we know that we have 4 moles of C2H2 if we punch out this first calculation. So now that we know the moles of acetylene, to calculate the heat of reaction, we're going to take the moles of our limiting reagent times the enthalpy. We have 4 moles of acetylene, and we know that we have 2,599 kilojoules of heat generated for how many moles of acetylene that react. How many moles of acetylene are reacting in this given chemical equation? In this given chemical equation. How many moles of acetylene are reacting in that given chemical equation? What's the coefficient for acetylene? Don't be shy to type it in the chat. It's not too much of a trick question. What was that? 2, exactly. We get the 2 from our stoichiometric coefficient. Remember, our enthalpy is written in terms of the overall enthalpy over the stoichiometric coefficient of whatever reactant you're looking at. In this case, since we're calculating the enthalpy using the moles of acetylene, we have to use the enthalpy in terms of kilojoules of energy generated per mole of acetylene that reacts. Does this idea make sense to everyone? Does this make sense to everyone so far? Okay, and that in turn gives us a heat of reaction of negative 5,198 kilojoules. To calculate the work, we have negative P delta V. So looking at our pressure, it's 1 atmosphere. So we have 1 atmosphere. Our delta V is negative 144.2 liters. And we know that we have 101 joule per liter atmosphere and 1 kilojoule per 10 to the third joules. That in turn gives us a work value equal to 14.56 kilojoules. And in turn, if we calculate our change in internal energy, which is equal to heat plus work, that gives us 5,198 kilojoules plus 14.56 kilojoules, which gives us, in the end, 5,183 kilojoules for this exact reaction. That's the change in internal energy for this reaction. Any questions in the chat? Let me just see. So it's not a coincidence. You can convert the moles of acetylene into the moles of another reactant or product. However, your limiting reactant for this reaction will always be acetylene. And I would recommend doing your conversions utilizing the moles of your limiting reactant just to minimize the number of steps. But yes, if I gave you the amount of product generated, you could, of course, calculate the enthalpy using the moles of product just as easily. Yeah. Did that make sense? Any questions on this example? So expect to see from these difficult problems that we've covered, expect to see maybe 1 or 2 of those on your final, and or on your exam 3. Any questions on this example? Really don't be shy to ask. I don't see where you, I don't see in your, I don't see in the problem we aren't given the mass of carbon dioxide. You can calculate it certainly using the limiting reactant, and then you can use that to complete the remainder of the problem. But I think it's just simpler to figure out the limiting reactant and then use the moles of limiting reactant to calculate the energy or heat of reaction. Does that make sense?
So pretty much what I'm confused is like how you figured out the moles of H2O.
Yeah, that's arbitrary. You can pick any product you want.
Right. Instead,
Yeah.
so I did carbon dioxide, and that's what I'm saying.
I see. Yes, then that's perfectly fine. If you said acetylene is limiting, we make this much carbon dioxide, and you use that throughout your calculation. 4 moles of acetylene into the moles of carbon dioxide. And that's perfectly fine. You can do that. It will work just as well.
Okay, and for the Q reaction, we still use that C2H2 because that's the limiting reactant.
Yes, but you can just as easily use any other reactant as long as your moles are of the limiting reactant or the product. I prefer using the limiting reactant in this calculation because there's less of a chance that you'd plug in a number of moles that is not from the limiting reagent. So like if you plugged in the moles of oxygen unmodified, the answer wouldn't be correct. But if you plugged in the moles of acetylene or any of the products, your answer would be fine. Does that make sense?
Okay, cool. Yeah, thank you.
Mm-hmm.
Appreciate it.
Any other questions that I can address? If not, let's continue on and let's discuss Hess's law now. So Hess's law is an application of state functions. So let's work on this basic idea. A reaction can be expressed as a series of steps. Okay, that sounds like a state function to me. Then the enthalpy of reaction for the overall reaction is the sum of the enthalpy of reaction for each individual step. So let's look at the following example. So let's pretend we wanted to know the enthalpy of the following reaction. We can think of this reaction as a series of discrete steps. So this would be step 1, this would be step 2. And at the end of our reaction, if we add both of these discrete steps together and we add their enthalpies together, we in turn can describe any reaction we want in terms of these individual steps. So for example, in this case, we're looking at this overall reaction here. We can break this overall reaction into 2 unique steps. And by adding our reactions and our enthalpies together, we can calculate the enthalpy for this reaction. Okay, so let's showcase this graphically just to show what's going on here. So initially, we have iron solid and oxygen gas, okay? And we're going to iron oxide, okay? For the first step, our enthalpy is negative 822.2 kilojoules. Okay, so this is our first step. We made iron oxide. Okay, and in our second step, we've taken our iron oxide and we've reacted it with aluminum solid to generate aluminum oxide and iron solid. So as the iron is present both at the start and end of our reaction steps, we can cancel the iron. The iron oxide that we made in one step was consumed in another step. So if we add our 2 chemical reactions together, and if we add our 2 enthalpies together, we get an overall reaction. In our overall reaction, we've taken aluminum solid plus oxygen gas, and we've generated aluminum oxide solid. And this enthalpy is equal to the enthalpy of step 1 plus the enthalpy of step 2. So does this idea that we can express a reaction in terms of any number of steps, and that if we add our steps together and we get an overall reaction, we can calculate the enthalpy for that overall reaction? And the reason why this works, the reason why Hess's law works, is that state functions only depend on the initial and final states. Thus, we can draw a path using any steps as long as we go from initial to final. So as long as our individual steps get us from our initial to our final state, we can draw any individual steps that we want. Does this idea make sense? Does it make sense when you look at a picture of what this is looking like graphically? Does everyone see how if we add up our steps, we've gone from initial to final? Can I get some feedback in the chat, just how comfortable everyone is with this idea? So let's talk a little bit about how we can apply Hess's law. So we can model reactions in terms of any number of individual steps. We often visualize Hess's law using what are known as enthalpy diagrams. So again, enthalpy is a state function. An enthalpy diagram indicates each step and the enthalpy of each step needed to go from reactants to products. So an enthalpy diagram is a tool to calculate the overall enthalpy of reaction or the enthalpy of a physical process from tabulated enthalpy values. Now, what's really important to note is that the enthalpy diagram is not describing the actual steps in the reaction. They're describing a series of steps that would get us from the reactants to the products. In reality, the reaction can take an entirely different path, but it doesn't matter. We don't actually need to know the actual path the reaction takes. We only need to know what is the difference in energy between our initial and final states. And that is the beauty, that is the power of state functions. So again, just to draw a picture, so in our individual steps, so once again, so we have step 1 and step 2. In step 1, we have iron solid reacting with oxygen gas to yield iron 3 oxide. So this is our first step. Our enthalpy is equal to negative 822.2 kilojoules. And our product from this is iron 3 oxide. Okay. Now for our second step, we are reacting with aluminum solid to generate aluminum oxide solid and 2 iron solid. And this step has an enthalpy of negative 848 kilojoules. So if we add our steps together, net, our iron cancels. Our iron oxide is just an intermediate that is neither in the reactant nor product side of our final expression. Net, we have an equation where we've taken aluminum plus oxygen, and we've generated as our final product aluminum oxide solid. And our delta H is equal to the enthalpy of step 1 plus the enthalpy of step 2. Does this make sense to everyone? Does everyone see how if we add our steps together, our overall enthalpy matches the enthalpy of our overall reaction?
Can you explain again why you canceled out that iron at the end and in
Ah,
the beginning?
yes. Ah, yes. So looking at iron, it's present on our reactant and our product side, right?
Right.
So then, has iron really undergone any change in this reaction?
Not at all.
Not at all. Exactly. So just like in net ionic equations, and just like when we added redox reactions together, we can cancel species that are identical in terms of formula and physical state on both sides of our reaction equation.
Okay.
Does that
Yeah,
make
that makes sense. Perfect.
It's the same reason why the iron oxide isn't appearing in this equation, because we make our iron oxide and then we use it up immediately.
Okay. Cool, cool, cool. Thank you.
Okay, perfect. So let's talk about how we can apply Hess's law. And let's talk about some rules about how do we add thermochemical reactions. So our goal in this entire process is to generate the desired equation from the given chemical equations. So let's look at some relationships involving the enthalpy of reaction. So when an equation is reversed, the sign of your enthalpy of reaction is multiplied by -1. So to help you visualize what's going on here, so let's pretend we're looking at the following reaction. So carbon plus oxygen is leading to carbon dioxide. So this has an enthalpy of -393 kilojoules. Okay. So, whoops, one moment. Let me just rewrite that. Oh, never mind, it's back. Okay. If we went the exact opposite direction, if we went from carbon dioxide to carbon plus oxygen, we know this gap is 393 kilojoules. So then if we went from this lower energy system to a higher energy state, would our enthalpy be positive or negative? Allow me one moment just to correct what's going on here. Okay, so to go from carbon and oxygen to carbon dioxide, our enthalpy is -393 kilojoules. So to go in the opposite direction, the enthalpy would be positive. It's the same reaction, except run in the opposite direction. So if this first reaction releases energy, the reverse reaction would absorb energy. So if you reverse a chemical equation, the enthalpy also gets reversed. So the enthalpy of our forward reaction is equal to negative enthalpy of reverse reaction. Does everyone see graphically why that makes sense? If to go from reactant to product, you go down in energy, you release energy. To go from product to reactant, you must go up in energy. Okay, in terms of adding equations, just like in redox reactions, chemical species that are present on both sides of an equation with identical physical states and charges can be canceled. So for example, this carbonic acid is present on both sides, so I'm going to cancel that. For water, we can also cancel molecules of water on each side to give us the following complete equation. Yes, so going back up would be the decomposition of carbon dioxide to carbon and oxygen. Yes, that's exactly right. Did that address your question in the chat? Perfect. Okay, so we're used to canceling species with identical formulas and physical states on each side. And now as our last rule, if the coefficients of an equation are multiplied or divided by the same factor, the value of your enthalpy must be multiplied or divided by that factor. So for example, if I'm multiplying all of my coefficients by 2, my enthalpy also gets multiplied by 2. Does that make sense to everyone so far? Okay, so these are the rules in our toolkit. Let's talk next about our strategy for adding reactions together. So suppose we want to calculate the enthalpy change for the following reaction, and we're given these two component reactions. So our first step is to choose the most complex compound in the desired equation. So I'm going to put a circle around this hydrazine. Just as a side note, hydrazine is the principal component of rocket fuel. And I'm going to find a given chemical equation that contains that compound. Okay? So I put a box around hydrazine. Okay? Now what we have to do is we have to adjust the coefficients or reverse the chemical equation so that the compound is on the appropriate side of the equation and has the appropriate coefficient. So, is hydrazine on the correct side of our chemical equation in our given equation? So if I want my given equation to match my desired equation, it's not on the right side. So then, what do I have to do to this reaction? What do I have to do? Do I have to flip it? Do I have to change the coefficients? What do I have to do? Do I have to reverse it, or do I have to change the coefficients? Ah, you're one step ahead. Yes, we will have to multiply our enthalpy by -1 because we are going to reverse this reaction. And I always like to write what I'm doing on the side there. So I just said reverse. Okay, so that tells me I have to reverse my equation. So that gives us 2 ammonia leads to hydrogen gas plus N2H4 gas. And our enthalpy is equal to negative 187.8 times -1. That gives us an enthalpy of positive 187.8 kilojoules. Okay, we're making progress. So now we write out our modified chemical equation. Now, what we have to do is we're next going to look at our modified chemical equation. Okay, and we're going to look for the next most complex compound present in my first chemical equation, but not present in my final equation. Okay, so let's look. So looking at this equation right here, let's compare it to our desired equation. So our desired equation, let's write that out. We have 2 hydrogen plus nitrogen leads to N2H4. Okay, and now my question to all of you is, I'd like you to just spot the differences between our desired equation and our current equation. So what species, what compounds are present in our current equation that we want to get rid of? Which ones are present in our current equation that are not present in our desired equation? Yep, so we want to get rid of this ammonia, and we also want to get rid of this hydrogen as well. Okay, so we want to get rid of these things. So what we're going to do next, is we're going to choose an equation containing these intermediates, and we're going to adjust our coefficients and reverse the chemical equation so that the intermediate cancels out. Okay, so let's show what I mean. So in our starting equation, we have 2 ammonia leads to H2 plus N2H4. This, we have our enthalpy. We have our enthalpy of 187.8 kilojoules. We're going to go up to our chemical equation, and we see we have another equation given that has our ammonia and it has our hydrogen, okay? Now, looking at our given equation, if we wanted to cancel our ammonia, we would need our ammonia to be on the opposite side, okay? So this is our goal. We want our ammonia, and we need two ammonias on the right-hand side. So then, based on that information, what do we do to the second equation? If we want to cancel ammonia, what do we need to do to this second equation? Do we need to adjust a coefficient? Do we need to flip it? How do we cancel our ammonias? What are we going to do? So again, we have this equation. We want this equation below in purple. And so to cancel ammonia, we need ammonia on the right-hand side. So we found an equation that has ammonia. We want to get rid of ammonia using this equation. So what side do we need this ammonia on? If we need it on the right-hand side, if we need these two ammonias on the right-hand side, do we need to do anything to this equation? Do we need to do anything to this equation? Or does it have what we need? Does this equation have what we need to cancel our ammonia? Yep, we've already used the top equation, and looking at the bottom equation, it has the ammonia as well that we need to cancel out. So what we're going to do is, if we look at our bottom equation, we see that it has the ammonia that we need to cancel out, and it also has the hydrogen that we need to cancel out. So we're just going to write out our bottom equation as written. So we have 3H2 plus N2 leads to 2NH3, and we're going to write down its enthalpy. So it's 92.4. And as we see, if we try to add our equations together, the ammonia cancels and our undesired hydrogen cancels. So that in turn gives us, when we add our two equations together, we're also adding our enthalpies, and that gives us 2H2 plus N2 leads to N2H4. This matches our desired equation, and our enthalpy is equal to 182.2 minus 92.4 kilojoules, which gives us an enthalpy of 90.4 kilojoules. So this is how we've calculated the enthalpy of this unknown reaction using the given enthalpies for two or more known reactions. So just to summarize what we've done, okay, so all the way from the start, here's our desired equation up top. We find the most complicated species, which is hydrazine, and we modify one of our equations to put the most complicated species on the correct side of our chemical equation. So that required us to reverse this first reaction. We reversed the first reaction and we modified its enthalpy. The enthalpy got multiplied by -1. Now, we have some unnecessary compounds in this chemical equation. So we need to add another equation in order to cancel out our undesired intermediates. So to do that, we identified ammonia and hydrogen as undesired compounds on the wrong side of our chemical equation. So we went up and we found another equation that had ammonia and hydrogen, and we modified this equation. So ammonia and hydrogen are on the side opposite, so that when we add our equations together, the ammonia and the hydrogen cancels. Notice how if the ammonia is on the opposite side, when we add our equations together, they cancel. So now that we have our second equation established, we write out our second equation, and then we add our reactions together. We cancel our like terms, and we add our enthalpies together as well. After adding our equations together and verifying we have the desired equation, we add our enthalpies together, and this total enthalpy value gives us the enthalpy of this desired reaction. Does that make sense to everyone? Does that make sense to everyone so far? Any questions on this example? So we'll do a few more examples of Hess's law. We'll do a lot of problem solving sessions on Hess's law in our supplemental lecture in laboratory. I wanted to introduce the concept of Hess's law in this first moment. Then we're going to take a quick 45-minute break, and we'll resume this supplemental lecture in laboratory. So I'll see everyone at 12:45 in laboratory, and we'll continue this discussion.